Hi, this is Sudeep and I welcome you back to this wonderful journey of learning structure analysis with StatPro. If you are new to this channel, welcome. Please do hit the subscribe button and do hit the bell icon for more notifications from the Structure Insider channel. In the last session, we have deducted the principal axis system and the principal moment of inertias from the values of moment of inertia and the product of inertias that was available for a fixed set of centroidal axes. We have learned three things in the process. Number one, the principal axis, there are two principal axes which has the maximum and the minimum moment of inertias about it respectively. Number two, the product of inertia about the principal axis are zero. And number three is that the principal axes are spaced 90 degrees apart from each other. So this is a channel section, okay, this one. And let Z axis be the axis of symmetry of the channel section. An axis of symmetry would mean that it divides the section into two similar halves. Now, remember that in one of our last sessions, we said that the product of inertia would disappear about the axis of symmetry. To see that session in details, you can click on the link above. Now, we have also said that the product of inertia would vanish for an axis that is a principal axis. To see that in details, you can click again on the link that is appearing now above. Now, this would mean what? This would mean that the axis of symmetry of this singly symmetric section. Now, why are we calling this a singly symmetric? Because this is the only axis about which this section is symmetric. It's not symmetric about the y-axis. So now, since the product of inertia about the axis of symmetry disappears and also the product of inertia about the principal axis disappears, this would mean that the axis of symmetry is one of the principal axes of a singly symmetric section. Now, on the other hand, we have also said that the other principal axis, remember that there were two principal axes, the other principal axis would be located at 90 degrees away from this particular principal axis. So this would mean that this y-axis, which is at perpendicular to the z-axis, is actually the other principal axis of the singly symmetric section. Now, consider a doubly symmetric section like an I section. Now, in this case, both of these axes that are depicted here are the axis of symmetry. Now, since there are two axes that are symmetrical axis or axis of symmetry, we call this as a doubly symmetric cross section. Now, for a doubly symmetric cross section, it is very clear that both the axes of symmetry would represent the principal axis of inertia. So in the past few sessions, you would have noticed that when I was finding the moment of inertia about any axis, I was pre-assuming that the beam was bending about an angle of symmetry. So in other words, what I was trying to do was I was trying to find the moment of inertia about the principal axis to maximize the utilization of the material. But what would we do in case we have a section like an angle section which is unsymmetrical and where it wouldn't be easy to find out the axis of symmetry? So we will see in a moment. All right, so we will start with this problem which relates to an angle section. This problem is taken from the book Solid Mechanics by Igor P. Popov, and the problem statement is that we want to find the principal axis of this angle section and the moment of inertia about the principal axis. Now, note that this is not a singly symmetric or a doubly symmetric section, right? So we intend to find out this is actually an angle section which is an unsymmetrical section. So how do we find out the principal axis for this. Okay, the first step involves to finding out where this CG point is. So the first thing that we do is calculate the location of CG. And how do we do that? Okay, now we take this, the CG of this particular area. So we take this full leg here. So then the area of this element here would be 200, which is the depth, multiplied by 20, right? And we are trying to find out the CG from the bottom of the bottom flange. So for this element, the CG from the bottom of the bottom flange would be 100 meters. So that is multiplied by 100. And then we want to find out the area for the bottom flange here. Now we already have considered this portion, so we shouldn't be considering it. So 100 minus 20, so we have to consider 80 meter length and 20 meter of thickness. So the area would be 80 multiplied by 20, and the location of the CG from the bottom of the bottom flange would be 20 by 2, which is 10 millimeters, right? And the area of the whole angle section would be given as, so equal to, so that's the area of the whole angle section would be given as this one. So the area of this element plus the area of this element, and this would give, y bar would be the distance of the resultant area from the bottom of the bottom flange. Now if you calculate this, you'd see that the distance comes to 74.3 millimeters. So this means that this distance here is 74.3. Now there is another aspect that we need to find out, where, so we know that CG is at this distance from the bottom of the bottom flange. Now let us see where the CG is from the left of this side flange here. So how do we calculate that? We calculate, again, it's the same thing. We would calculate that as 200 into 20 into, now this whole area is at a distance of 20 by 2 from the left of this vertical flange. So that would be into 10 plus this area, that would be 80 into 20. So 80 multiplied by 20 would be this area, and the distance would be 20 meters plus, so this one is 80, 80 by 2 would be 40, 40 plus 20 would be 60. So it would be 60, and that would be equal to, again we would find out the value of this thing. So this would come out to be 5,600 millimeters square. So 5,600 millimeters square, and we are measuring along the z-axis. So let us take that as z bar. So now this would come to, I have already done the calculation before, so I'm just putting down the numbers. By now you are aware, when we solve the parallel axis theorem, you are aware as to how we would need to calculate the distance, or how we would need to locate the CG. So I haven't shown the calculation in detail. If you want to see the details of this calculation, you can go to the session where we solved 2 problems with parallel axis theorem by clicking on the link that would be appearing in the screen above. Right. Now, this means that we have this value calculated as 24.3. Okay, so now that we have identified this, what we would do, we would, now we have located the CG, now we could actually remove this calculation from here. Now, y and z axis are called the geometric axis of a cross section, of this angle section, sorry. And we can calculate the IZ value using the parallel axis theorem, right? So again, it would be, we'll take this as one element and this as the other element. So IZ would be calculated. So about this Z axis that goes through the section. So it can be using the parallel axis theorem, you know, for this element, it will be so this is the moment of inertia of this stem about its own centroidal axis, and add that to the product of the area of this element into the square of the distance from the CG. What is the square of the distance from the CG? Well, it would be 24.3. So, well, wait. It would be, we are actually calculating it about the z-axis. So, it would be 200 by 2, that is 100. 100 minus 74.3, that would come to 25.7. Multiply that with the square, and then will come for this particular element, which is, so the moment of inertia about this element about its own centroidal axis is this. Sorry, there was a mistake, I guess. It would be, so this is about the z-axis. So actually the cube should be here. I'm sorry about that. The cube should be here. So in this case, though, it would be about, so remember that the parallel axis theorem says that it has to be about a parallel axis. So the centroidal axis parallel to this z-axis, right? So that would mean that the cube would be on 200, not 20. So that's 200 cube by 20. But in this case, it's okay. It's not 100 though, because we already have considered this whole element. So we are only considering this element. So it is 80 into 20 cube by 12. And then we add that to the area of that element. The area of that element, so it would be 80 into 20 into the distance would be 74.3 minus 10, right? 74.3 minus 10, so it would be 64.3. How is it 10? Because the CG would, the centroidal axis about this individual element parallel to this z-axis would pass through the center of this particular element, which is 10 meter from the bottom plane. So 74.3 minus 10 would give 64.3. And this brings us, I have already, as I've said that I already did the calculation before. This brings us to 22.65 into 10 to the power 6 millimeter to the power 4. Okay, so I write the value of IZ here, that is, let me write it here, 22.65 into 10 to the power 6 millimeter to the power 4. Now similarly for IY, so to find the moment of inertia about this axis. Now you have to find the moment of, for parallel axis theorem, you have to find out the moment of inertia about this element, about a parallel axis to y-axis going through its own centroid. So in this case, now the cube would be on the value of 20, plus it would be the area multiplied by, now what's the difference here? 24 minus 3 minus 10, right? 24 minus 3 minus 10 would be 14.3. So it would be 14.3 square. And then for this, the centroidal axis would be passing through somewhere around here. So it would be, now in this case, we have the cube over 80 into 20 by 12 plus 80 into 20, right? And that's the area multiplied by the square of the distance. So this would be now 80 into 20. So this distance would be what? This distance would be, so 80, so half of it, 40, plus 10 is 50. 50 minus 24.3. Sorry, about the y-axis. So, okay, 20 into 80 cubed by 12 plus 20 into 80 cubed by 12, and we have, this one is 80. So, this would be 40. So 40 plus 10 is 50. 50 minus 24.3. 50 minus 24.3 would come to 35.7. So it would be 35.7 square. So this would mean that the value of Iy would be 3.85 into 10 to the power 6 millimeter to the power 4. So we have calculated the value as 3.85 into 10 to the power 6 to the millimeter 4. So we are calculating the moment of inertia about its geometrical axis z and y. Now there's another thing that we need to find, and that's the product of inertia. And how do we find that? So let me rub this off since we have recorded the values here. So now we will calculate the product of inertia. Now we will use the transfer formula for product of inertia. Now if you haven't seen that session in details, you could look into the details of the transfer formula for product of inertia by clicking on the link above. But what it is that the product of inertia for each of these elements about its own centroidal axis would vanish because it's a symmetrical section. So all that would remain is, for each of the element we have to calculate the area. So for this element it is 20 into 200, that's the area, multiplied by the distance of its centroid from the overall section centroid. So then it would be 24, the product of, so multiply the area with 24.3 minus then the centroidal axis parallel to this axis would be minus 10. So 24.3 minus 10 would be 14.3. And then the centroidal axis of this individual element is located at 100 millimeters from the bottom of the bottom flange. So 100 minus 74.3 would give the distance of the centroid from the centroidal axis of the whole section. So 100 minus 74.3 would be 25.7. And then for this particular element again, the area multiplied by, remember that again for this area, the product of inertia about its own central axis would vanish because that's an axis of symmetry for that particular element. So we'll get that as 35.7 so this one would actually be a negative distance, but let us keep that positive. 35.7 into 64.3. So that would give the value of product of inertia as this one. Okay, now let us record this value here. So we have calculated the moment of inertia about z-axis, about y-axis, and about this, and for this axis system we have calculated the product of inertia as now. The next thing that we want to do is to calculate the principal moment of inertia, right? So how do we calculate the principal moment of inertia? Well, remember the equation that we have used in the last session, or we have derived in the last session. So if you do not remember what that expression is or how we have derived that expression, you can go to that session by clicking on the link that is appearing above. So I1 would be given by two. So you and add that with square root of and you just substitute these values that we have recorded here, and that will give you the major principal axis moment of inertia as similarly for the moment of inertia about the minor principal axis. All that you need to do is and if you substitute these values again, this would come to so we now know the moment of inertia about the major principal axis and the moment of inertia about the minor principal axis. Now, but where is this principal axis? That's the question, right? So how can we find that out? Okay, all that we need to do is to solve for this equation. Tan inverse of 2Iyz by Iz minus Iy. That's all that, and we substitute these values from here for all the values that we have derived for the geometric section, and you will calculate that as tan inverse of 0.547, which would give the angle as 28.68 degrees, which would mean that theta dash would have a value of 14.34 degrees. So a positive value of theta dash would indicate that the axis the principal axis is located by going a value of theta dash which is in the anti-clockwise direction. So basically then, what we now know about the principal axis is that if we locate so this at 14.34 degrees, and this is the major principal axis that we have located, and the minor principal axis of course would be located perpendicular to that particular axis. So it's just we need to find out the value that is perpendicular to it, and this will come something like this. So this one we represent, this axis we represent as 2, this one as 1. So this one is the major principal axis and this one is the minor principal axis, tilted at 14.34 degrees from their geometrical axis. So I hope the concept of principal axis is absolutely clear now. If you have any doubts, do ask them in the comment section below. And how does this relate to the modeling of properties in StatPro? Well, we will find out in the next few sessions. If you think that I have added value in this particular session, please do hit the like button so that it reaches out to many more who would be trying to find out a similar content. See you in the next video. Till then, bye-bye.